Well, good day, everybody, and welcome to the Neuroscience edition of 5-Minute Psych. In this 5-minute segment, we'll look at the resting potential, or understanding the state of the neuron when it's at rest. In doing so, we'll look at two forces that contribute to the negative resting potential by acting on three key molecules that are concentrated in and around the neuron. When a neuron is in its resting, balanced state, it's negatively charged at minus 70 millivolts. Think of a neuron as being covered by a skin called a membrane, and inside and outside of the neuron is fluid that is filled with electrically charged molecules. Here, we're looking at a cross view of a membrane along the axon, and you can see some positively charged sodium ions, symbolized by Na+, located mainly outside of the neuron. Also some positively charged potassium ions, symbolized by K+, mostly inside the neuron. And then there are some negatively charged organic ions, symbolized by A-, that are inside the neuron. And so what this negative charge boils down to is the fact that the inside of the neuron has more negative ions than the outside, or the outside has more positive relative to the inside. Now, although the negative charge of a neuron at rest is only teeny tiny, it's only 71,000th of a volt, you still have to wonder how this is the balanced state, to hold a negative charge inside the neuron relative to the outside. Well, the answer lies in two forces that act on the ions to create this distribution. And these forces are concentration gradient, also known as diffusion in some places, and electrostatic pressure. Concentration gradient is the tendency for ions, which are always in motion, to distribute themselves evenly in their environment. So ions will always move from an area of high concentration to an area of low concentration. You can test this yourself tonight. If you go to bed, drop a teaspoon of sugar into a glass of water. You'll see the clump of sugar float to the bottom. In the morning, it will all be evenly distributed, even if you didn't stir it. With electrostatic pressure, this is the tendency for ions to attract other ions with opposite charges and to repel ions with the same charge. You can test this yourself with two magnets. Try to hold the sides of the same charge together, and you can't. But turn one magnet around so you have a negative lined up with a positive, and they'll be drawn to each other. The ions in our neurons act the same way. So how do these two forces lead to the negative resting potential? Well, all along the neuron's membrane are doors that are specific to each ion. So sodium has its own doors, as does potassium. These doors are called voltage-gated ion channels because when the inside of the neuron reaches a certain voltage, those doors will open for that ion. Now, organic ions don't have any doors, and that means they're stuck inside the neuron forever. Because they have a negative charge, they certainly contribute to the negative resting potential of a neuron. Potassium has doors that are relatively easy to open, and so potassium can flow in and out of the neuron freely. However, because it's mostly concentrated inside the neuron, the concentration gradient wants to push it outside. But at the same time, because it has a positive charge, it's attracted to the negative charge on the inside. As such, potassium pretty much stays inside the neuron. Now, sodium is a very special case. It is also positively charged, but it's concentrated outside of the neuron. This means that both forces would be pushing sodium to come in, begging sodium to come in. But the sodium doors are stuck, and sodium can't come inside. Plus, each neuron is equipped with a sodium-potassium pump that works continually to kick out 3 sodium ions in exchange for 2 potassium ions. This excess of positive on the outside from sodium, combined with the negative organic molecules on the inside, means the inside of the cell has a negative charge relative to the outside. We just looked at how the forces of concentration gradient and electrostatic pressure create the negative resting potential of the neuron, which will help you understand how neurons communicate or the action potential. Aren't you glad you had 5 minutes?